I'm going to briefly introduce our recent work using Federated approximant, which is a tool in numerical analysis to develop the federated learning algorithm. As we all know, OHDSI is an example of distributed research network, including data partners across worldwide, and PCORNet is not another one in US, and PZET is also a distributed research network for pediatric population specifically, and it has multiple children's hospitals across US. And there are several benefits to use the information from distributed research network to generate clinical evidence. For example, we will have more generalizable findings by including more representative population. We will have larger amount of data with higher statistical efficiency, and we will be able to study rare events, for example, the adverse event from drugs or rare diseases. But there will be also challenges, for example, when we are sharing information across data partners, we will need to be worried about the patient's privacy, and we will worry about the communication cost. And there is also a unique challenge in studying rare diseases I will introduce in a minute. For example, we are interested in comparing the depression drugs on rare adverse events using these 4 databases in OHDSI, and these are the 3 comparisons we are interested. Some outcomes are very rare. For example, for the last comparison, we have 2 databases with 0 counts in the target treatment group. And one common approach to estimate the comparative effect is that we will first apply the propensity score stratification to adjust for confounding variables. And it can be a list of high-dimensional confounding variables, including demographics, prior conditions, exposures, and center. And after that, we consider within each propensity score stratum, these confounding variables are relatively balanced, and we will condition on these propensity score stratum to conduct outcome regression. For example, we can use the stratified Cox regression with the stratum-specific baseline hazard function, while the treatment effect, the parameter of interest, will be shared across strata and across database. Then our goal is to estimate these treatment effect, these parameter theta using the multiple databases. The unique challenge comes from the situation with rare events. For example, when we have few or 0 events, the likelihood of the database will be ill-behaved. For example, when we're using Cox regression and there is 0 count in some treatment group, the partial likelihood will be monotonic. In this case, if we just use the meta-analysis to take weighted average of these maximum likelihood estimates, the result will have substantial bias due to these unstable estimates. And the key idea of this federated learning algorithm is that we will approximate and communicate the local likelihood function of each database, and then we can combine this likelihood function to a global likelihood function at a master site and conduct further analysis. One idea is what if we just communicate the local likelihood functions on grids, but it can be costly because we need to ensure the grid is fine enough for accurate estimation. Another idea is what if we use simplified function to approximate these local likelihood functions, and maybe we can just communicate the parameters associated with these simplified functions. And there is a previous work by Martin and co-authors focusing on the Cox regression with small and 0 counts, and they provided a few options to approximate the partial likelihood of the Cox regression. And in our paper, we just look into the approximation theory, and we would like to find some methods that can be generally useful for regression models, not only the Cox regression. For example, we can use quadratic approximation to approximate our likelihood function. It is easily obtained through the Taylor expansion, but the issue is that the quadratic functions always need to be symmetric, which is not our situation when we have rare events. Then we look into the Federated approximant, which is developed by Qiong since last century, and it is called the best approximation of a function near a specific point of a given order. And the Federated approximant is actually a rational function, and the order 2-2 Federated approximant we used in the paper is actually a ratio of 2 quadratic functions. After we looked at the performance of the Federated approximant, we found that it can approximate our true likelihood function very well, even in scenarios when we have few events or 0 events. For example, in these 2 plots, we use the solid line for true likelihood function, and this dashed cyan line for the approximant and dashed red line for the quadratic approximation. And the Qiong approximants always are close to the true likelihood function, even we have only one event in the control group or zero event in the control group. Based on that, we developed our Fed-Padé algorithm. In this algorithm, we will require each database to calculate 5 numbers, which are the higher order derivatives of their local likelihood function at an initial estimate of the parameter. And with these 5 numbers from each database, we can then reconstruct the approximation of the global likelihood function in the master side. Then we can just optimize this approximate likelihood function to get the point estimate, or we can just inverse the likelihood ratio test to obtain the confidence interval. In the paper, we also offered the option for random effect setting, where we didn't assume the parameter, the treatment effect, to be exactly the same across database, but it can follow a common prior distribution. The key idea for the random effect setting is pretty similar. For each database, we will approximate the likelihood function using the Padé approximant, which can be summarized using 6 parameters. And with these 6 numbers from each database, we can then reconstruct the likelihood function for each site at the master side, and then we can conduct further analysis for the parameters in the random effects models. Yeah, that's all I have. Thank you for your time, and thank OHDSI for the opportunity to present our work here. And here is a screenshot of our paper.